So, good morning. Yes, my talk is about form and energy, so architecture, energy, urban design and energy, how energy can influence form. Architecture is responsible for half of the world's energy consumption, roughly, so it is and can be a large part of the solution. Energy design is basically working with natural forces. For example, here in Baku, a windy city, Azerbaijan, using the wind, which is normally a problem for skyscraper design, harnessing the wind to drive natural ventilation systems. In Shenzhen, near Hong Kong, using natural light in buildings where light is normally the problem, so exhibition buildings. Bringing the light in a controlled way, diffuse light controlled by a multi-layered roof construction, controlling natural forces. These projects are with Copimobile, another one in Dalian, so again, natural light for a conference center, again, spaces which are normally devoid of natural daylight. With Marias Talibo Architects in Barcelona, we developed this. It's also been built at the moment in Shanghai. Here we're using the forces of the heat from people. So each one of us here today is basically emitting 100 watts continuously of heat energy, which normally we do nothing with except use it to employ the cooling system. Here we're using the heat basically to drive a natural force of thermal buoyancy to create the airflows necessary for the ventilation of the building. Another natural ventilation concept in New York, this time you see on the bottom right the natural ventilation function articulated in the building skin. This is an older project in Giza, Egypt, the Great Egyptian Museum. And this one is a low-tech solution where we basically have a large stone roof made of black stone. It gets really hot, of course, in the desert sun. The air from the exhibition space then flows through a special construction through this stone roof. The air is deliberately heated, so we have hot air as a product, and the hot air is used to drive a relatively simple system with desiccant cooling to cool the building. So the more the natural force of the sun hits the building in the desert, the more we can cool it with this force. So it's basically taking the natural forces and re-diverting them, re-employing them to basically solve the problem they seem to create. We also look at nature and copy things which work well in nature. For example, when we get hot, we perspire. Other animals, some animals too. That means we use the water evaporation to cool the building. So this building was a building which was built by Dualis System, a pavilion, Expo 2000 in Hanover. And they asked us to do a building which basically has no air conditioning system. So it was with Atelier Bruckner from Stuttgart. So a building without air conditioning, how do you do it? And we know, of course, we can use brick, we can use stone, we can use concrete, so thermal mass, and then flush it at nighttime with cool air and cool down the thermal mass. But this approach, which works well on many buildings, is not a good approach for a building for 6 months in an expo. So basically we created this building using water as thermal mass. So it's a lightweight construction, you fill it up with water. The other thing the client wanted was to take the building down after the expo and build it somewhere else. So basically you take it apart, you fill it back up with water at the new location. So water becomes easily transportable thermal mass. The next thing, of course, is that this mass has to be regenerated in terms of the energy has to be taken out, and so it can provide cooling for the next day. This occurs, as I said, by perspiration. So basically the building sweats. So at nighttime, it perspires, we spray the water into the atmosphere, it cools by evaporation, we collect it at the bottom of the building, and the cooling energy is ready for the next day. At the start of the day, we heard about buildings which give. So buildings which don't just take, because this is the way we think, and now we're sort of getting a little bit more efficient, and we want our buildings to take less energy, less water. But in a way, we have to have a paradigm change and think about buildings which give back, which here, for example, in Montenegro, we developed this master plan with Ortner and Ortner, where basically a major part of it's a peninsula which was to be developed, and the state of Montenegro said if you develop this to the foreign real estate developer, it has to become zero carbon. So it gave us a chance to rethink the whole system. Integral part of the whole thing is an energy grid which connects the mobility system, which is electrical taxis, with the buildings which produce solar and wind energy. And energy storage is a major component of the future. And in this case, it's the mobility system, which is integrated with the buildings, with all the batteries, which provide the virtual energy storage system. We also pump water to to the higher parts of the topography and use stored water as mass, which is potential energy. So introducing integrated systems and buildings which produce more than they need to use themselves. Here for Singapore, with Koh Phi Phi, this is the form of a skyscraper, so a vertical typology at the equator, so it gets very little sun on the facades. So therefore, the special form, which was developed to have these solar blades generate energy all year round, while at the same time not mutually shading each other, allowing daylight into the building to the occupants and allowing views, of course, out. So the forms develop from the specific challenges which we face at different locations, different tasks. Smart skins is a major area of research in the last years. Basically here we're developing a skin, so a facade which can change, where we can change all of the changeable variables in the facade building physics variables, and also integrating the intelligence in the system so that the system knows not only the present inside-outside conditions, but also the future predicted conditions. Weather forecasts, but also self-learning algorithms about how people use the building, and therefore can in real time achieve the highest performance possible theoretically. And we show that you can increase the energy efficiency by 90% compared to energy efficient facades today. Already 20 years ago, we have this approach, so we don't achieve the performances, of course, achievable in the research project yet, but this is where buildings built here. This is one with Schneider and Schumacher. So a double skin, which you see reacts to external conditions, so reacts to light, to temperature. On the right-hand side, it starts to open up when it gets warmer, metamorphosis of architectural form. And also because, of course, the facade is more expensive and more complicated, it allowed us, though, on the other side, to use low-tech systems to heat and cool the building and natural ventilation, so we could prove to the client it's also economical, which is, of course, all of these buildings are buildings which get built, most of them. This one is in Austria, not far from here, in Well, so again with the same architect, again with a dynamic skin reacting to external environments. European Central Bank was a project we won with Koh Phi Phi in 2003. And over the years, it was completed a couple of years ago, we developed a smart skin where we have selective coatings to deal with light and heat, movable shading elements within these modules. Also, you can hardly make it out in the pictures, but natural ventilation elements which are working with the wind pressure in a high-rise environment. And this building, of course, presents a more monolithical, homogeneous appearance, so different than the one which is moving in Frankfurt. So smart skins, but not influencing necessarily or allowing different architectural languages. Form follows energy is basically the hypothesis that when we work like this with teams, architect and engineer together from the start, and energy is one of the parameters, we come up with new forms. And there's always somehow a central question, sometimes several, that is driving the form. So for here, that was Gateway Gardens in Frankfurt. The question was, it's near an airport, it's a really bad environment, a harsh environment from the airport, from the Autobahn. So how does this building breathe? How does the building get air? Of course, how do the occupants get air? And so we developed this form by introducing to the mass two atria. One is delivering the fresh air, the other is taking out the extract air, taking the air in at the top. And basically from there we developed these forms, of course, spatial connectivity in a skyscraper and other issues too. And from there the design proceeds. Adidas, this is a company, of course, you all know, based in a really small place in Germany. And they had a competition. And in Germany, the conventional, in Europe, you could say, the conventional wisdom of office buildings, you build them narrow for daylight and for natural ventilation. After studying the brief, working here with Delegate Meisel, we very quickly realized, of course, Adidas, and we went to see them, and they're all running around in tracksuits and runners, and we realized, of course, it's not a typical German organization, so they need a different kind of building. So thinking about these issues, and thinking about also the energy performance, we developed a very deep typology, so really contrary to conventional wisdom in German design. Not a narrow plan, a very deep plan, almost 40 meters deep. The whole basically is a spatial volume in which we insert platforms, so that's a three-dimensional working environment. So when you're in the building, you're basically everywhere. And proving also that the energy performance is better than conventional typologies for this company because on the one hand, the compactness of the building form is an advantage. The other hand, we have the whole roof as an energy surface, as an energy generating surface. So these are about configuration. It's becoming very important in our work in recent years. So how you configure, basically, I think is the most interesting area in architecture and energy. How you configure the spatial programs, how you put it together. This one's in Vienna, so in this city with Carsten Roth architects from Hamburg. This was a bank building. So the conventional solution here would be this perimeter block. Then you can have a courtyard or an atrium. I was pushing in the first workshop for an atrium because of energy, compactness, but also for communication. But realizing that these typologies, all the conventional typologies, have problems. One of them being people are either looking into the courtyard or the atrium or outside. And many other things too, which we know from building the buildings. And therefore, in the first workshop, we basically came up with a new typology. So we have this concentrated working space outside. We build this large communicative atrium in the middle, and we inserted all the special functions into this, and basically working with energy performance in the forefront, develop a new typology of an office building. Or another example with Ortner, this is again about configuration. So Ortner, and this was in Duisburg, an archive building. So a building basically to store government papers, German government papers, valuable documents, hygroscopic, so they get damaged if the humidity is not constant. Therefore, we use normally air conditioning systems. We found the old corn storage building on the site, and we had to keep it. So originally, we thought about making the windows bigger because they were quite small to get more light in. Again, thinking about the program relatively early on in the first weeks of the competition, we said, why don't we basically brick up all of the windows, so actually close up all of the windows, organize the organization of the client's business differently. So we put the archive into the old corn storage building. We put the people into a new building alongside. By doing that, we take out, by bricking up the facade, we take out the external loads, so the sun and the light. By taking the people out, and they only go in to get the documents they're working on and then work on them somewhere else, we take out the internal loads, the people, the computers, the lights. And then we could show with the thermal mass of the building, we can maintain the stable climate necessary for the archive without any active systems. And basically the most important decision there was this original decision to tell the client, you've got to change the way you configure your spatial program, which was a competition, which was risky, but it worked. This is in Graz with Riegler Riva Architects, Medical University. Again, configuration. In this case, for example, the urban form is used. Graz has not much wind, so the form allows the wind to flow to the city, which is important for the urban area of Graz. Then how we position the offices and laboratories in this dense urban configuration is an important issue. And how we placed on the bottom right the daylight openings, so the windows. So as you go deeper into this urban configuration, the windows get bigger. As you go down, it gets bigger. As you go up and out, they become smaller, so they react to the light condition. Configuration, of course, also of the mechanical system. So it's basically form, skin, systems, energy supply. Another university, this time in Paris, with OMA architects, with Rem Koolhaas, we worked on how to develop a campus basically in a climate envelope. So basically putting the whole university inside a climate envelope, generating these important spaces between the program where people meet and communicate informally, which we know to be very important in universities. At the same time, conceiving the whole thing as an energy machinery where we bring the various program items together in a symbiotic way. So the excessive heat from the laboratories, which is normally leaves the building all year round, we use basically, by bringing them together, the excessive heat to flow into this hall space, to create this macroclimate, which generates a different way of communication on a campus in Paris, reduces the heating load of the offices. So again, a new typology where energy is also informing the process. And then how we evaluate these things is also of huge importance to architecture, and most architects don't realize that this is something which is going to influence the whole future of architecture. So all these certification systems and energy passport systems, basically very, very simple systems which tell you your building uses too much energy. Energy efficiency is not about just energy demand, how much a building uses. It's also about what the qualities in the building are. And so I invented this system years ago, where you can actually measure the actual energy performance of a building. So it tells you what the quality of the space is compared to the energy demand you use to create it. The difference is we come to different architectural solutions. So this is why it's so important that architects involve themselves with how architecture is evaluated and don't allow architecture to be evaluated in a simple, banal way. Urban design research, for example, here, what interests me in the last years is the question of urban density. So we all talk about urban density the last 10 years and how it has to be increased, but I was asking at some stage the question, at what stage does it get too dense? So can we become too dense in an energy sense? And what you find out is, of course, transport energy reduces with increasing density. Building energy goes up because the buildings get higher and deeper. Renewable energy, because of mutual shading, becomes less. So somewhere there's this sweet point, this point of optimal urban density. So we studied various typologies. And when you compare them all, what you do is, if you make very dense urban conglomerations, you need huge energy fields outside to supply them in the future, with solar energy, with wind energy. Therefore, when you introduce energy into this discussion and realize by less complex structures, you can integrate the energy production into the skin of the building, the whole conversation of urban density shifts. And it's not just a question of density, 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 it's a question of integration. Therefore, we also look at the whole system. So here, for example, countries. Here's Austria, the energy schematic, how the whole thing works. When you study it, you realize this physical infrastructure, if we optimize it completely, so electrical cars, passive houses, photovoltaic on every single surface, we don't get from the 5,000 watts we use per person at the moment down to 2,000 watts, which is the goal for sustainable development. So basically, what this research tells us is that we need to reconfigure, rethink our physical infrastructure. Energy storage is a massive topic, of course, in the whole thing, not just producing and using energy, but storing it. So here, projects in China using water towers to store energy again. But in research, we then looked at how can we rethink the city? So we use all this virtual infrastructure we've built up in the last 20 years. Everyone's using it. We can work anywhere we want. A lot of people already use these possibilities, but we still build the cities like we did 100 years ago. Exactly the same way, as if all of this virtual infrastructure didn't exist. Of course, we built some data centers and stuff to house all the equipment. This project is asking the question, if we use the virtual infrastructure really in a way which enables us to reconfigure the physical, how would the city of the future look? So office buildings becoming smaller, more communication centers, residential buildings allowing people also to work at home, reducing transport and other issues. So rethinking the city, and this shows very radically that we can achieve the goals of sustainability, but we need to rethink the whole picture. Symbiotic relationships, for example, is about nature, technology, people bringing them together in a way in which they benefit from each other. So here, a skyscraper designed for Seoul, the warm, moist air coming in on the left-hand side. It's cooled by groundwater, the condensed moisture flows to the vegetation, the cool, dry air flows to the people in the offices behind. So bringing nature into buildings in a way which is symbiotic. And then on a research level, rethinking the city again in a way in which even agriculture can be integrated into buildings. All of the symbiotic relationships that we can think of, instead of parallel processes, bring it together in thought models. Student projects, which were done many years ago, which look like architectural utopian projects, but are actually trying to solve these energy issues. And when I show this in Europe, people say, yeah, this is good for your projects in China, but we don't need it. Yeah, we're finished here, we just have to renovate. So therefore, I show always this simple sketch. 50 years from now, if we continue as we are doing now, basically a little bit more new build here, a little bit renovation there, tear a little building down here, on that corner. In 50 years from now, half of the buildings that will then be there are buildings that are yet to be built. So even in a city like Vienna or Frankfurt, London, Paris, even in Europe, we have to have a master plan for the city of the future, because it will happen whether we design it or not. And therefore, each fragment we do now is a fragment of the city of the future. So we propose things like this in Berlin. This was Gleis Dreieck. So sometimes we do propose things. We know this was with Copimbala. We'll never going to win a competition in Berlin at the moment, but still important to make a statement on how we should really rethink how everything is put together. So form follows energy in the sense is a radical restructuring of the entire infrastructure of society, which is the research is showing. At the same time, it's on a building level possible today by introducing these themes to create buildings which have a much higher real energy performance, measured in quality and quantity, than the buildings that we have known up to now. So if you're interested, you can look at our homepages, the book, as already mentioned. Thank you very much for listening.